I'll go back and forth with Christian, but not enough videos.
Anybody have any questions? Anything exciting to exchange? Something you know about? Something you don't want me to know about that I should know about? Things like that.
You know that Kelly Patrick surgery?
I do. Minor outpatient, I think.
Yes.
Minor.
Okay.
It's a follow-up to the surgery she had when she broke her ankle a year ago.
You don't have to break it again, do they?
No,
Hey,
they don't have to remove the wire they put in there.
It was kind of
What's wrong? I'll be missing class in October.
I've never had surgery.
Should I email you
Yeah, me
all the
neither.
details and everything about that?
Yeah, just let me know.
Yeah.
I don't
Oh,
think.
really, really?
I gotta leave on Thursday night.
I don't think, just to kind of reiterate this point, when you're a professional, it doesn't mean that you're some sort of superhuman and you never mess up and you never make mistakes and you never have things happen. I don't know if y'all, a couple weeks ago I went out to start my truck to go to lunch and it didn't start. That stuff happens. But professionals communicate. And they do it as soon as they understand there's going to be a conflict, rather than waiting until after the fact. Very often students that have kind of a I work at McDonald's mentality, I'll let them know why I didn't come in tomorrow when I go back in and expect to still have a job. And that doesn't fly too well in a professional setting. So I kind of hold that line on purpose. Let's see where we are.
I
I don't really know where we are.
My last name is vegetable oil and apple.
2.5 years.
Yeah.
My last name is.
But I think we finished that.
I think we finished
Well,
the
I
slides.
have written down this all right.
All right.
We finished the slides.
Oh, that's right. Yeah, Thursday, Friday.
So let's start what would be right here, which feels like it's a little bit duplicated, but it kind of has to be that way. Because we're going to broaden the topics out a little bit and talk about something other than alkyds, but we're going to focus on alkyds a little bit in the beginning too, because we're going to talk structure. So this will get us back around to some alkyd calculations. So when it comes to the mechanism, I'm going to leave it up to you to fight for your right to know tetrahedral intermediates and things like that. All right? Direct polyesterification is the most typical method when we make materials for coatings. It's also very common for PET and things like that. Except that PET very often now will dive into an ester exchange. Who knows what ester exchange is? That's where we would use a large excess of one reagent. In the case of PET, we make the dimethanol ester, terephthalic acid. And because you use a large excess, you can easily get to a high percentage of ester early. And then it turns out actually I said that wrong. They don't use the methanolic ester. They use the diethylene glycol ester. And then they strip off ethylene glycol. So you use a large excess of this. It's the brand new pin. Apparently not. So you make this at a 2-to-1, and I think they even run it at 4-to-1 at times because they're fully set up to do recycling. So they do the 4-to-1. You get a large excess of ethylene glycol, and with that large excess, you make these esters quick. Now, energy of activation to make an ester, there's a cost, there's a barrier, but energy of activation to do esterification, there's not. So what do we do then? Then we take this trimer as designed, we put it in, and we strip ethylene glycol. And that is something we already have on hand. We're recycling it. We already know how to recycle it. We've used excess here. We strip it off. And as we strip it off, we are just doing transesterification, which means we're no longer giving up water. We're not getting rid of water. All that's finished. So you have great compatibility. You have very early, high degree of conversion of acid groups, and you have a large excess of hydroxyl groups. Now you can see where you could make trimer, pentamer, septamer, that sort of thing. But that's the ester exchange. Transacylation is usually reserved for some specialty materials. Polyarolates usually are the ones we would make that way. And then acylation, which is the thionyl chloride or phosgene round to getting acid chloride. So mechanistically, what's important as I go through these next 4 slides real quick, direct polyesterification typically uses acid, metal, or metal oxides or salts. And the one that's most common for high temperature synthesis is tin oxide. Now there's lots of other tins that are used, but when you do very high temperature reactions, you use tin oxide. And that tin oxide actually rearranges to become like the salt, not the salt, but the adduct of, you'll see this later, where you've got tin in some form here with terephthalic acid or isophthalic acid. So you put tin oxide and in situ, it rearranges to be the diester of one of the acids. And when that happens, then the tin is soluble. It's soluble in the system. It's not a heterogeneous phase reaction, and the tin has activity. But the tin still doesn't catalyze esterification until you get above about 220 C. So the tin is a horrible catalyst if you're going to do aliphatic systems, because the only reason we take systems, there's 2 reasons we take systems to really high temperatures. One is we want to do it fast. And 2 is the monomers aren't soluble, so we have to use temperature to make things homogenized. Terephthalic, isophthalic acids are just not soluble. And you'll see this when we make polyester on Monday. We'll use terephthalic acid or isophthalic acid probably in a blend. And as we start the synthesis, it's all hazy, it's turbid. We haven't intentionally added water, but there is some water in there. And then we warm it up and we see some water come off and we think we're making progress and it's still turbid. And then all of a sudden, at some degree of conversion, probably right around 35 to 50%, the entire reaction will go clear. And it goes clear because we finally made enough dimer so that the acid that's not soluble in the rest of the mix becomes soluble in all of it through a homogenization process, or a compatibilization process. When we have this, like if we have anything sensitive here on R, temperature-wise, and we're going to run this reaction at, let's say, 90 C. It's possible to make it at 90 C. If we're going to run it at 90 C, then we use an acid catalyst. If you use sulfuric acid, for example, it's a very good catalyst, but it tends to add color. We don't want color in everything we make. If you add color, then you got to compensate for it when you make something somewhere else that you want to be white. You can't make it white enough, and that turns out to be problematic. So resins with a lot of color can't make pastels and light color unless they're yellow. People get tired of making yellow or buying yellow.
So what was that color with it?
Sulfuric acid as a catalyst. You'll actually start to get some sulfate adducts, and you'll get chromophores from that. Sometimes people have determined that those are parts of the aromatic ring, sometimes not. But sulfuric acid is an excellent catalyst for low temperature systems, but only in low doses. If you put too much in, you instantly get color. It kind of, I don't know if you've ever played with sulfuric acid, but you can put it on almost any carbon compound. You just put a couple drops on a piece of wood and it will char it. So, just to get a feel for that color, the color bodying. Now, I want to digress for a moment mechanistically, because we always talk about catalyst here. Obviously, these are self-catalyzed, but that changes the order of the reaction, right? It becomes it's dependent on the acid concentration, so as we go to higher and higher conversions, the acid concentration is diminishing, so we become less and less catalyzed, which is a bit of a mistake. So you drop a little bit of catalyst in and you overcome that. But I want to draw something that a lot of people are not aware of. When I was at Bayer, one of the things that was really neat is they had a full-on research group, and the research group was trying to figure out how to make polyesters at a low temperature, so they had no thermal byproducts, no side reactions, none. And they developed, with another company, a ceramic tube. And this ceramic tube had porosity that was just right for water molecules to fit out of. So it's like a molecular sieve. talk about molecular sieves, we're usually talking about a 1.5 angstrom molecular sieve. We pour those into something. Matter of fact, you could pour molecular sieves into a blend of ethylene glycol and PET and terephthalic acid. And if the two were soluble, you could make polyester at ambient, but only a little bit, because the molecular sieves just won't quite drive it enough. Okay? But because water will fit in that molecular sieve, it will work. So they made this system where there was a porosity here so that they could flow monomers down this tube at ambient temperature. And as they flowed down, as they made this path, molecular weight went up. Now, the tube was, there's one example where it was a quarter-mile long.
I was gonna say, like, how long does that tube need to be?
And then, of course, you had this other issue, right, where if you put solvent in, which you have to if you're going to make high molecular weight material, otherwise you've got to add heat. If you add heat, you're kind of defeating part of the purpose. But then they also pulled a vacuum here. This space had a vacuum pulled on it. This is part of a series of German patents they developed. They can make polyesters at ambient. At ambient. Pull the vacuum, get a negative pressure here. The only thing that will volatilize is, if you don't have solvent, the only thing that will volatilize that comes out of that, if you get the porosity right, is water. Therefore, you can make polyesters. They had to add solvent. The solvent had to be big solvent, so it wouldn't fit out. You didn't want things to clog the pores. You had all these other issues. But you could make aliphatic polyesters relatively easy. It's kind of neat. Now, I want you to cement that, because lots of people go, and Charlie McCormick's one who in seminar will go, well, it's not easy to make polyesters because at 180 degrees C, everything's being destroyed. Well, that's BS. I just want to call it out right there, because I get tired of hearing it. People make PET at 220 in the solid state all the time. Every day of the week. You're holding it in your hand. It functions. It works well. There's no byproducts. There's no issues. There's no color. So let's use some factual data from the world around us and move forward. Okay? You can make polyesters at ambient. You can make polyesters at 100 C. You can make them at 53 C by direct esterification. You can throw in lipases, and we've done synthesis inside a glassy matrix, TG 58 degrees. The film has enzymes in it. We put raw materials to make esters inside, free acids and free alcohols, inside the film. We cast the film. We touch it. We feel it. It's solid. It's a glass. And we make esters inside that film. Okay, so don't let anybody fool you. Esterification is an effective, it's even a natural process, right? People in California should be going, yeah, dude, esters, they're all natural. Right? Right, Greg?
Absolutely. And they process PET to about 500 F.
Oh, yeah.
Yeah, and
absolutely.
Like 510, and it doesn't char at all, and it comes out nice and clear.
It has to be dried to a certain
less
parts
than
per
50
million,
ppm.
and it has to be under a certain head of nitrogen or argon or something like that. But it's possible. But throw some oxygen and water in there, and everything goes to hell quick.
I've done that.
So, this is just one of those things that people miss. They don't get that, because we always talk about high temperature. So when we do ester exchange, and here's two examples. This one has phenolic in group, that has methanol in group. And what we're going to do is strip off the alcohol. Then we make esters that way. We tend to use weak alkali catalysts like metal hydroxide or sodium hydroxide would work, for example. You'll see that in a few cases. You'll see this in this slide, you'll see it in the next one. This is pretty corrosive. So when you're removing that, people worry about removing that and the fact that it's going to be acidic in nature. And here's the same way. This is the opposite. Instead of making alcohol what we have in excess and volatilizes, we have the acetate or acetic acid. We're stripping off acetic acid, it's corrosive, and as it's pulling that off, you're obviously corroding whatever reactor you're in. But this tends to use metal acetate as your catalyst. And we'll see some of those examples in a few slides. All right.
Can you go back, please? I want to write down what kind of catalyst or one more.
We do have to pause, let's see, tomorrow at some point and make a decision on what we want to make for our polyester. So I think what we'll do is I'll come prepared tomorrow with a list of raw materials we have. And y'all will have to guide the mighty pen so that we do the polyester calculations and figure out what we want to make on Monday. And I think if we stick with mainly aliphatic raw materials, we can start the polymerization at like 7:30 in the morning on Tuesday, and I think we can be finished by 6 or 7 p.m. on Tuesday. Okay, so we don't have to go through the night. If we use the aromatics, it takes so much longer to get them to clear, to get to that conversion, that we wouldn't be able to do that. Somebody'd have to be here every couple of hours, and since I know the burden would fall on those that are key to my lab to be up all night, that is an unfair positioning for my students who will run an aliphatic version. Although I'm sure they are willing and fully capable. All right. I did try to share some slides, but apparently I got confused about which sets came from which. So I'll get that straight and share some slides so y'all have them. Okay. Notice that this is bisphenol A. And I don't have too many holy cow pet peeves. I don't think I do anyway. But this and this functional group and this functional group are not the same. And each year, at least one graduate student stands up and professes that this will react just like that. This one cannot rearrange to be this, which there's a question mark about that when you do it this way. Technically, it should move over here, right? You can see how that could happen. And this is an excellent leaving group. This is not an excellent leaving group when it comes to making esters. Please don't just look and say, oh, it's hydroxyl. There's more to it. There's more that matters. Look into the chemistry. Look at the molecule. Think about all of the details. With that said, if we try to make a polyester with this as our diol, the diphenol, and we put in any aliphatic alcohols, this will dissociate in a transesterification type mechanism to form the anion and become an acidic solution. And when it becomes an acidic solution, we are hydrolyzing, or we are catalyzing hydrolysis if there's any moisture around. That will happen even at ambient on materials that have TGs above the ambient. Okay. This is the acid chloride. We've seen it before. Conditions are the same as what we saw at the end of the oil section. You want the slide, that's fine. I guess there's not slide numbers. Maybe there are. I think there are. This isn't even the right slide set. When I had that error, I grabbed another set, an older version, when those chemical structures went away on it. So this one has the chemical structures, but it was the most recent, so I opened the most recent. But this isn't the right set. This This isn't what Stephanie and I worked on this summer. This section will be fine, but when we get to later, it'll be different. We won't make it that far today, so it'll be okay. The number's still not easily visible, is it?
Well, I think we only applied
Yeah, probably fine.
You've got to go into the design and then into the theme color slide. You can see it though.
It makes you feel like you're kind of cryptographically figuring it out. Yeah, only move the one. Okay. I'm gonna move forward. Okay, in the world of polyesters, let's get the lay of the land. We've got oil-free polyesters, and we've got oil-modified polyesters. We focus a lot on oil-modified polyesters because it's one of the dominant coatings classes that's used, or raw material classes that's used in coatings. But in the rest of the world, unsaturated polyesters are used to do a lot of things like structural function. Bless you. And saturated systems are used in coatings and other areas, some of those being hydroxy functional, some of those simply being thermoplastic materials. A lot of people don't know it, for example, but a lot of exterior tent fabrics are polyester. Feels like nylon. If you think it's nylon, everybody assumes it's nylon, but it's polyester. It happens to, polyester tends to, with the typical sets of monomers we use to make tent material, polyesters tend to photodegrade slower, so they last a little longer. Nylons are a little tougher, they have a little higher tensile strength, that sort of thing. But as far as classes go, we have oil-free and we have oil-modified. And these materials, the unsaturated materials that we're talking about here, are predominantly from maleic anhydride and fumaric acid. And those are very distinct monomers that we put in the backbone, because what we're doing is we're taking maleic anhydride and we're polymerizing it in so that we have a carbonyl activated double bond. And a carbonyl activated double bond means that we have enough electron withdrawing where this will co-polymerize with styrene, methylmethacrylate, and things like that. This is rarely used in the coatings world. It has been used, and the main area it is used is what we would call gel coats. Gel coats are usually where we've made the jet ski hull, and we want something that's very similar to that to be highly cross-linked and kind of seal that fiber-laden composite from the water so the capillary forces take longer to pull water in and become equilibrated with a load of water. One time we had a group in, give you a feel for composite structures, and the U.S. Coast Guard will buy like a bayliner, a 30-foot bayliner, and they'll retrofit it and mount their guns on it and all their specialty equipment. What they do is they buy a finished bayliner that's in perfectly good condition, and then they drill a bunch of holes in it and knock out plugs. You know what knockout plug is like? If you were making a doorknob hole where you pop a plug out so you can run pipes through it and stuff. And then they put that boat in the water and they run it for a year, then they bring it back out and they weigh it, and it's like 24% heavier. It took on 24% water. It's a lot of extra fuel. But all these holes they put in there expose a bunch of free fibers. The fibers suck water in. You got to think about it. It's not that different than our arterial network, right? If you expose it, things start to systemically make their way in through those, just like in a tree. Cut the bark off a tree. So they need to buy ships or boats that already have all those things built into the design, or they end up taking on all this water. It's in these two categories. I think I've already covered this, but unsaturated, it says here maleic and fumaric. And the most common reactive diluent there is, if you imagine, if this is a high molecular weight polyester that has that repeat unit and then some other repeat unit, whatever it might be, the viscosity of this system could be really high. So let's say this is a 10,000 molecular weight system, and it has 8 of those in the backbone. Pretty high molecular weight for a polyester. Well, what we do is we make that polyester, and while it's warm, under controlled conditions, we would cool it down, and we would blend in styrene as a solvent. But styrene is also reactive, so we don't call it a solvent, but I want you to hear it that way because it's what reduces the viscosity of this material so that it's workable, it's pourable, and you would go to the store and buy it. It would be in a can that would say fiberglass resin. You'd pour that out, and instantly you'd smell styrene. Burn your nose. But they co-polymerize. The styrene polymerizes through these double bonds. They get a co-reaction. And that's what builds the molecular weight and crossing density.
Say it would lower the viscosity.
When you add styrene? Yeah. But it's not polystyrene. It's styrene monomer.
So it's basically just disrupts the.
It's a solvent.
Yeah.
Styrene monomer is a good solvent. But in this case, we call it a reactive diluent. Because it's not going to, in the main, it's not going to volatilize like a solvent. It's going to react into the network. Now, I say in the main because if you've ever approached a production facility that uses the site material, or if you've ever caught a whiff of something in the hall when LeBeau is in there making some of his composites, you're inhaling styrene, monomer. That's what that smell is. That offensive smell he puts out. That's one of his offensive smells. Yes, so you know, there's a problem here, and when there's a problem, there's a good opportunity for scientists. Everybody in the world would like to replace styrene monomer with something else that is equally as good as a solvent and equally as good as a co-reactant, and yet that does not seem to exist readily. There is a cost barrier here. Styrene is pretty low cost. So there are some acrylate monomers we could pick that would approach that, but they would be 4 to 8 times the cost. And most people are not willing to pay 4 to 8 times the cost for a jet ski of what they currently are. Not that that would be the total cost. All right, let's start here and look at some actual structures. Polyesters from the reaction of an oil, polyhydric alcohols, and polyfunctional acids. This is the single largest quantity of solvent-soluble polymers manufactured for the coatings industry. This is real important to you because these are design criteria. When the world goes to the shelf and wants to buy an alkyd, they say, oh, I've always used a very long oil polyester, and that's all I use on the furniture I make. And then other people would say, oh, I don't care, just guide me. And they say, well, what are you going to use it for? You know, do you want it to dry by auto-oxidation? And you say, oh, well, I'd like the option of it drying by auto-oxidation, or I'd like to cure it with an external crosslinker. I'd like to do both with one system. Well, typically that puts you in the medium oil. Because if you get less oil than this, the oil is not effective in concentration terms sufficiently to get good crossing density. So you don't get a good delta TG, so you don't get good molecular weight buildup, so you're not tack-free. But at the same time, this has enough free hydroxyl groups if we design it properly, so those hydroxyl groups can react with other entities like melamines or isocyanates. So we put the definition up here. Oil length is expressed as the percentage of mass of fatty acid triglycerides. So it doesn't matter if it comes from the fatty acid process like we did in the help session, or if it comes from oil. Total solid resin. So you've got to take out all the non-volatiles by fat and get down to solids on solids comparison. Remember these numbers for design purposes. Let's take a look at some structures. These very long oils are almost completely restricted to the printing ink industry. And we're going to make a lot of shifts as we go across this spectrum from very long oil to oil-free. We're going to make a shift in how we use them. We're going to make a shift in which monomers we're allowed to use. We're obviously going to make a shift in the percentages of different monomers that we use based on the definition. Right? The reason the printing ink industry likes these so much is they can say that they're using natural products, but they can also achieve very low viscosities by having a high amount of oil. If you have 75% oil, by definition, you must be pretty low molecular weight. You can only be so high molecular weight. That would, Harmon, that would be an excellent test question, actually. How high could the molecular weight be if you're 75% oil? How high could it be? There is a limit. If we gave a given set of monomers, it could only be so high. Which means you're self-limited, right, by design. We'll come back around to that again and start to do some calculations. So the most common here would be linseed, and we almost always use only true drying oils. The disruptor there is that soy is a much stronger lobby group than the United States. So the soybean board, or the soy growers association, whatever they call themselves this year, the politically motivated group to sell more soy is what I like to call it. They want all ink to be soy-based. So they do their best to not have linseed oil, because linseed oil is not grown in the United States. Not in my knowledge. It could be, but it's not a major crop. The other part to remember is these systems, by definition, have to rely. They have to rely upon auto-oxidation. In the name, we're looking at 870. What do we come up with? 878 molecular weight. Is about what an oil is. Typical oil. 878 grams per mole for a triglyceride. It's all aliphatic. The TG, by definition, can't be 300 C. The TG is below room temperature. We couldn't pour it. And when we pour it, if we want to have anything that's tack-free, we need some auto-oxidation. So you see how this goes hand in hand. These are things that are very intuitive once you look at the chemistry and understand the purpose, the rhyme, the reason, the how we use it. A very long oil, non-drying oil-based polyesters are used as plasticizers. So when we put castor oil in and we want to plasticize, we can make very long oils. So this is an exception to this class of materials. And mainly used in ethyl cellulose and nitrocellulose, where the celluloses tend to be very brittle materials by nature. Modified celluloses tend to be brittle, but they're also excellent film formers. So we still like to use them to get depth of image, distinctness of image, depth of image. But we often need plasticizers to keep them from shattering when we bump them with a golf cart or a shopping cart or something like that. And the non-drying oils like castor oil tend to be very compatible. Compatibility is a big deal. All right, so this is a typical example of what we would start with. So this is real. People made this for generations. There are families that built the wealth of the entire family on 6 or 7 formulas like this. Okay? So you on a desert island could now grab some nuts and seeds and do some chemistry and some crude methodology. You can kind of understand what you have. You can make this. Start a small company. Maybe you find some coconuts. Stuff like that. Substitute some glycerol. Don't you keep TMP in your first aid kit?
I will know.
So basically what we have is we extend the oil slightly by using trimethylpropane, penterithrotol, acetylic acid, tromylithium anhydride. We'll come to all these structures if you don't know them yet. And then we use lithium hydroxide as a catalyst. Not much of it either. You end up, in this example, you end up having about 10 to 15% excess hydroxyl groups. And you end up with 75% oil by weight. But those are actual gram charges. And then what I'd ask you to do on the test is, with this charge, what would you make? And you kind of go through and calculate it. You can see why the test could take a little while, right? So here we go. Let's step back. Here's linseed oil, lithium hydroxide, trimethyl propane. This first step is called alcoholysis. Alcoholysis is pretty important in that this is how we break these esters and rearrange so that we have a structure that looks like this, which we would call the monoglyceride. One ester in the glycerol molecule, and that makes this an AA monomer. But we also have two of these monoglycerides, but they're really not glycerol. But it'd be the mono substituted. So at a 2-to-1 ratio, we end up with 3 monoglycerides, or 3 AA monomers, to grow linearly with some branched side chains that are fatty acids. A question I've asked before on some tests, and it's a good one to think about, is if I put a dividing line here, class, if y'all wrap up your writing real quick and go ahead and finish it, but I want you to really engage in this because it's important. I talked about you yesterday when I was teaching. I talked about my creep comment and how it came back to haunt me this year because I didn't know you were in the room. But I had to use the example of polyethylene creep because someone asked why thermoplastics don't work in places thermosets in all applications. And I said, well, every once in a while something creeps in. So y'all are well thought of. I'm talking about y'all. If we draw a dividing line here, though, let's do this. I won't put anybody in the chair, but let's go in order. Let me ask a question. Draw this dividing line. Let's talk about what's above the line first. How many esters exist above the line in that combination of materials? Forget about the catalyst. 3 esters, right? How many free hydroxyl groups exist above the line? Well, it's 2 of them, right? So 6. Is that right? 6. Okay. How many fatty acids exist above the line?
1.
Above the line. 1 mole of triglyceride.
3.
Triglyceride. 1, 2, 3. Okay. How many moles of TMP exist above the line? 2. How many moles of glycerol are there above the line? Not free glycerol, glycerol based. 1. All right. Now let's flip this around. Let's go below the line. How many fatty acids are there below the line? Remember, there's a number here. See? 3. What was that in Inglourious Bastards where Germans do 3s different than British or something?
Yeah.
And he knew he was lying. All right, the big whopper, the big test. How many esters are below the line? All right. How many free hydroxyls are there below the line? You know. 6. How many T and P molecules are there below the line? The residue. Yeah, 2. Okay, are y'all getting the picture here? This reaction turns out to be very problematic. How do we know when it's done? Oh, I didn't finish. What's the acid number above the line and below the line? Theoretically. 0. You need to know why. Is the hydroxyl value above the line and below the line the same? It's the same above, the hydroxyl value. Hydroxyl value is not 0 though. Acid value is. Theoretically. The hydroxyl value is whatever the mass of all this is, and there's 6 hydroxyl groups. So you can calculate that, right? Brennan, did we lose water above the line? Did we lose water below the line? No. There's no mass change. All right. Greg, what kind of reaction are we running?
Transesterification.
Transesterification. No water loss, no mass gain, no change. All we're doing is rearranging. So I ask you again, how do we know when this is finished? And probably only carbon. So you can get lucky if the secondary is what ends up being dissociated first, and in some conditions it would be, in other conditions you'd end up with an amalgam, so it wouldn't be definitive by itself. So if we don't have an NMR, even IR turns out to be problematic, because we have the ester of CH2O, which is almost identical, right? It's almost identical in nature. This reaction is hard. It's easy to run, but it's very difficult to understand when you're finished. This is kind of a neat experiment for me and for you. Now y'all think about it. You know, you turn it in like a one sheet of paper tomorrow, and turn it in like a homework assignment. This is how I would do it. Okay? I'll leave you lingering. I like cliffhanger. So let's look at the reaction as it proceeds. We run the alcoholysis step, and this is an individual step. It's called that, alcoholysis. In the next step, we take those monoglycerides, right? And we would add acid intermediates in there to control the final molecular weight. And in this case, we add a monofunctional, and what we're trying to do is keep from having too much molecular weight buildup to where we would have a gelation issue. And you normally wouldn't have that problem except that you have pentoerythritol in the system. And pentoerythritol being tetrafunctional, you gotta like get me out of those pictures. Okay, good. The old Indian thing. Soul, taking my soul. My mom actually believes that. I'm always giving her a hard time about it too. I said, I got you on camera. You didn't even know it. Stealing my soul. Yes.
Is there a reason that you're using linoleic acid, or is it just kind of?
There is. In order for this alcoholysis step to work, you have to get to, and this is a practical thing, you have to get to an AA monomer. And you do that by adding more triol and then doing it at a 1:2 ratio like we showed on the prior slide. But then in order to have 75 weight% or greater of oil, of fatty acids, of oil residue, you can do the math on that monoglyceride and you can't get there. Because as soon as if you left this out, you can't get there. Just look at the original slide here with the numbers on it. Leave this out, and you have 578 linseed oil, and add these up. Somebody do quick math for me. That's 139, 49, 53, 200, and 205, 205 plus 578. You're right at 75, aren't you? But you're not quite there. The 578 is probably just a little below it. You're probably at like 72% if you left it out. So you just can't get enough oil in there by using oil alone and make that diol. And by definition, if you don't make that diol, then when you add the acid at this step, what will it react with? Well, you would transesterify, and I get that, but you would transesterify and have all sorts of problems. So you make that mono, let's write it first. You add this in to get your system adjusted for two reasons. One, to get the amount of oil up, and two, to keep this molecule, which is tetrafunctional, from causing some sort of premature gelation. And penterithiol can't be used at very high concentration. And then you have isotonic acid to grow it linearly from the diols. And you have trimethyltic anhydride, which is an interesting molecule in that you get half a mole of water here, right? You would react the per ester, and then you would react this. Your goal is still to have an acid value close to 0 and 10 to 15% excess hydroxyl, like we talked about before. You would continue to heat this until you got closer and closer to it, but you keep it at a maximum temperature of about 238. And in the end, you'd have a structure that looks kind of like this. This is a little bit of a simplistic, cartoonish version of it, but you see the residue of everything here as expected. And you see that penterithiol and, well actually, do we have, penterithiol is here. This gives you a lot of fatty acid per penterithiol, and then your trimethyltic anhydride also adds functionality. So your F average is pretty high here. It's a highly branched and short, choppy molecule with lots of fatty acids terminating it. So just as well, an excellent way to handle this for you as a test question would be to go, here's the cartoon. What should the charge be to make this molecule? And that's pretty straightforward, right? As long as you get a yield value, and you get a hydroxyl value, and you get those things. Yes, one of the problems with this cartoon is we don't have it drawn to show the excess hydroxyl. So you do need one OH in here somewhere.
Yeah, on the left side.
Oh, excellent. So it is there. Good. And it's drawn as the secondary. The secondary is harder to make, so it does actually end up being a likely hydroxyl to be there, all else being the same.
How do the barrier properties of these types of materials end with such branching? It seems like there'd be a lot of free volume within the matrix. Especially with such rigid.
Yeah, like trimethyltic anhydride is a planar structure with three.
Kind of bulky in the opposite.
But a lot of this is very flexible too, so I don't think you have a very long persistence length. But I don't think of alkyds as a real good barrier to it. What I haven't seen, Greg, is where somebody's really taken the time to quantify that. In wood coatings, we actually want barriers that are porous so that water, when the wood gets wet, it can breathe, right? And we know water is going to get in. So I think that people probably have taken advantage of this without actually quantifying it over generations. It would be water repellent, but it's not a barrier, right? So if you spilled water on it, you could knock it off and it wouldn't have soaked into the wood, but if the wood got wet, it could get out. Because when you put a really good barrier over wood, sometimes the wood will rot under the coating. You know, you've been in a bar before? Some of you maybe. You've been in a bar before where they have this really thick polyurethane? Those are great, as long as you wipe them down and keep them dry. But if you ever leave water long enough, cooled long enough so it gets in, the wood will probably rot below the urethane, and you'll actually see it like old rotten shit under the urethane coating. Because it's so thick, it actually does produce a barrier. Well, good question, because these things turn out to matter. How this structure contorts itself, and how much free volume is left in here. Now, what you do have an advantage here in this system that you don't in others is, this system has a low viscosity for a long period of time and has plenty of time to form its film before it vitrifies to still kind of relax into the right position. So there's not a lot of internal stress here until the late parts of auto-oxidation occur. All right, I got to stop there. I know y'all hate it. We'll have more time together tomorrow.